topic of what is an image. Here's an example of recent versions of what an image might be. These are neural radiance fields generated by taking sequences of photographs and combining them into an estimate of the radiance field from an object using a neural processor. Here's another example of an image, one of my personal favorites. This is the interactive gigapixel scale image taken with the DARPA AWARE cameras that had gigapixel resolution. And so this is also, of course, an interactive database. And so the image is not something that is easily printed and hung on the wall. It's an interactive data set that one can work with. So this course, we've been discussing how to form images with geometric fields and coherent fields, but the images we've looked at so far have been fairly rudimentary. Now we're ready to start dealing with photographic systems, which take gigapixel or terapixel scale data sets and transform them into ordered lists, images. Despite our interest in focusing on the multidimensional nature of image data sets, however, we need to understand the traditional way of understanding images, that a photograph is something like this, something you can print and hang on the wall, a two-dimensional object. So today we're going to review the process of forming two-dimensional images in photographic systems. Computational imaging.
Episode 49, Fourier analysis of focal imaging. Back in episode 36, we talked about this transformation. Transformation from a coherent field at the input plane, f of x, y, to the diffracted field, g of x double prime, y double prime, at an output plane as imaged through a lens. Now, the important thing to understand here is that we're talking about a transformation between fields. We have a field distribution on an input plane and a field distribution on an output plane. The field is 100% well-defined by its condition on a boundary. So if we say what the field is on a two-dimensional boundary, we can calculate the field everywhere. Episode 48, we talked about the transformation between objects and field distributions in the focal plane of a lens. The object is three-dimensional. It cannot be described by a distribution on a two-dimensional plane. So in episode 48, we talked about that three-dimensional transformation. Now, as we've seen, we actually have more dimensions. We have time, we have polarization, we have spectra. So this theme of multidimensional transformations is the central theme of the course. But as discussed in the introduction, for a long time, people think of photographs or images as two-dimensional things. That's really a limitation of physics and the way we print and hold photographs. There's no reason for it in the age of computational imaging, but it helps us to understand the basic process of two-dimensional image formation as we seek to use photography in systems, and certainly measurement on two-dimensional planes remains a central feature of imaging systems. So let's review what we saw in episode 36. We saw that this system can be described as a shift invariant linear system if we ignore the phase terms that we spent so much time discussing in chapter 5. But ignoring those phase terms, we see this impulse response is the Fourier transform of the pupil function evaluated at the spatial frequency x over lambda di. And so we had this transfer function description. So the spatial spectra of the diffracted field is the spatial spectra of the input field as modulated by the pupil function. It's a simple bandpass system. The impulse response is the Fourier transform of the pupil function, which for a circular aperture, defined here with aperture A, takes this form of the jink. So we get this standard area diffraction pattern as shown here. So at the top, this is a cross-section of the impulse response, and this is the two-dimensional impulse response, and this is the bandpass. The maximum spatial frequency pass is 1 over lambda f number over 2, and the width of the impulse response 0 to 0 is 2.44 times lambda f number. So f number again is the focal length divided by the aperture. Okay, so here we're done with talking with coherent fields. We want to talk about what if the distribution at the input and output planes is incoherent or partially coherent. The transformation from an input plane to an output plane for the cross-spectral density we've seen can be described using the coherent impulse response. So here we have the cross-spectral density on the input plane defined by variables x1, x2. We multiply by the impulse response at x1 and x2 and integrate over the input plane, and we've got the cross-spectral density at the output plane. The impulse response for propagation of the cross-spectral density is then the product of the coherent impulse responses at the variables that were interfering in the input plane and the cross-spectral density. That's pretty complicated, but again, as we've said, we're interested here in considering two-dimensional image formation. So let's assume that the input object is a two-dimensional power spectral density incoherent field at the input. So W of x1, x2 is S of xy delta x1 minus delta x2. In that case, this integral over x1, x2 collapses to a single integral over space, and x1 is equal to x2, so the incoherent impulse response becomes the magnitude squared of the coherent impulse response. Now, in the real world, there aren't very often two-dimensional incoherent distributions, right? The sources tend to be three-dimensional, in which case we got to go back to the three-dimensional transform we talked about in episode 48. But for a long time, photography has assumed that objects are two-dimensional, and this transformation describes the transformation from a two-dimensional incoherent source at an input plane to the two-dimensional image that it forms in the image space, with the impulse response being equal to the square of the coherent, magnitude squared of the coherent impulse response. Something magical happens when we do this, as we saw in our previous discussion of coherent imaging. We had these wonderful, beautiful phase terms out front that allowed us to use tychography to create a synthetic aperture. But if we take the magnitude squared, those phase terms go away. So we get that the incoherent impulse response is the magnitude squared of the shift invariant impulse response, which is again the Fourier transform of the pupil function. Now, since this h sub r, the coherent shift invariant impulse response, is the Fourier transform of the pupil function, the Fourier transform of the incoherent impulse response is the convolution of the Fourier transform of the coherent impulse response, which is the pupil function. So the incoherent impulse response is simply equal to the convolution of the pupil function with itself. Now, in a lot of cases, we're interested in comparing the relative transfer at different spatial frequencies. So this is often normalized to define what we call the optical transfer function, the OTF, which is the convolution of the pupil function divided by the value at 0. And it happens that at 0, we're just integrating the total magnitude squared of the pupil function. So the maximum of this incoherent impulse response is always at 0 frequency. It's a big difference from a coherent system where we could do high-pass filtering and block the low frequency terms. In an incoherent system, the maximum is always at the 0 of the shift of the pupil function, and so the maximum frequency transfer is always at 0 frequency. Okay, so let's look at the impulse response. This was our Airy pattern for the coherent function and for the coherent transformation, and now we're going to take the magnitude squared of this as the incoherent impulse response, and it looks like this. So basically, take the magnitude squared, things get the side lobes get suppressed a lot because they're not as big as the center lobe. And now if we look at the cross sections of that, you see something like this. On the left, this is the incoherent impulse response, the magnitude squared of the Airy pattern in cross section, and the frequency transfer looks like this. And now, because we're taking the convolution, so the pupil function had this square, but we take its convolution with itself, and the convolution, as you over here and have some overlap, and this distance is 1, the convolution extends out to twice the width of the underlying function, so it goes out to maximum spatial frequency of 1 over lambda f number. So x here is in units of lambda f number, and u is in units of 1 over lambda f number. All right, so that's how this two-dimensional imaging works. That basically an image formation is a low-pass filter operation, and the filter function is what we see here, and the basic process of imaging is to blur the two-dimensional input distribution. We can create different forms of the transfer function. When we talked about the coherent transfer function, we talked about an annular pupil where we block the center to increase the high frequency response. It's tempting to do something similar to that with incoherent imaging. Here's why it's tempting, is that we can use annular apertures with a folded lens, and so you can make the lens much thinner. Here's something like a 25 millimeter focal length lens, but packed into a 10 millimeter focal length path. And you see that because we've the entrance apertures here on the edges, the center is blocked to allow us to do this fold. We get a pupil function that includes an annulus, and so this is the diffraction limited response, or the diffraction limited optical transfer function. And here the frequency, the maximum is always zero frequency, but the midband is reduced, and the high frequencies are actually increased. They go beyond the diffraction limit for a clear aperture lens, which is a super interesting thing. So we are unable to just select only the high frequencies, but we can increase the high frequency response relative to the midband with this kind of lens. Throughout the remainder of the course, we'll discuss a variety of strategies for sampling that will use multiple apertures and other interesting optical designs. And so certainly this is something to have in our toolkit, the ability to make folded lenses that have a higher response at high frequencies. If you have this kind of annular lens, the impulse response looks like this. You see much more complicated, more side lobes, and you do see this is a relative transfer function at the high frequencies, can exceed what you would get for the diffraction limit. So a lot of this has to do with playing off of the relative signal to noise from various sampling strategies, as we'll see in coming discussions. If you look at what this does in an imaging system here on the left, we have a couple of images as our ground truth images. At the center is what happens to these images when they pass through a clear aperture. So now you see, again, it's very different from the kind of response we saw. We looked at similar images for a coherent system because the highest bandpass is always at the low frequencies. But here, so what's high frequencies here in the chirp falls off to, where the high frequencies are blocked. And in both cases, the square and the chirp are blurred. When we have an annular aperture, the low frequencies are passed, but here at the high frequencies, you see an improved high frequency response relative to the clear aperture system. Okay, so this is our basic introduction to two-dimensional photographic imaging. We'll talk at some length throughout the remainder of the course about ways to think about two-dimensional and three-dimensional imaging in these kinds of systems. One thing you'll notice is that we derived the optical transfer function based simply on the two-dimensional analysis that we had done with coherent fields. We didn't bring up this three-dimensional bandpass function that we talked about in episode 48, but we could have alternatively derived the two-dimensional bandpass as a projection of this three-dimensional bandpass. That comes up as a natural form when we have this term theta z. Theta z here is the defocus. What if we're not in a, so the underlying assumption we had in saying that our impulse response is the Airy pattern is that the system is in focus. But of course, systems may never be in perfect focus, and the object could be at any range, not necessarily the conjugate plane of the focus. So we can account for that by having this term theta z, which we saw last time we were going to define as 1 over z minus, we could define it as 1 over zi, 1 over zi plus 1 over z minus 1 over f. Now when we're in a focal plane, we assume this is 0, but if we're defocused, then that is not going to be 0, and our transformation will be more complex, and we'll be able to define this concept of a defocus impulse response that we'll talk about in our next episode. And we certainly recognize that objects are three-dimensional. So here you see an example from Wikipedia of focal stacking. On the left, we see an image focused on the fly. You see the fly's eyes in well focus. In the middle, we have an image focused on the leaf on the background. And on the right, we have an image which is synthesized from those two imagings, recognizing that the world is three-dimensional, and created an image where all the different ranges are in focus. And so we'll begin to talk about defocus and focal effects in our next episode.